Okay, so starting with the toroid again. So that is a recall. Toroid, what it is? A toroid is a donut-shaped, hollow circular ring with numerous tons of enabled wire coiled. Okay, coiled so close that there is no room between them when high inductance are required at low frequency. A toroid can be thought of as a circular solenoid utilized in an electric circuit as an inductor. What is an know better and more in more detail in AC chapter, alternate current. But that is the simplest. The last two lines are the simplest definition. A toroid can be thought as a circular solenoid utilized in an electric circuit as an inductor, or it is my solenoid look like, just wait. Suppose this is your one conductor, or in this particular conductor, if I wrap my wires like this, okay, so this is a solenoid. Yeah, this is my solenoid, current going in, current coming out. So if I just join my particular A end with particular B end, if I join this particular end with this particular end, so it can be look like this. Is this clear, everyone? So that is a toroid, nothing else. Okay, an infinite solenoid in the shape of a ring is known as toroid, and the magnetic field within a toroid may be calculated as follow: B equals to mu naught Ni by 2 pi r. Simple as that, because we have a magnetic field. Is study notes for electric potential capacitance available, sir? But you need to check. It is going to be yes. If you don't find, so let me know in the next lecture. Okay. Whatever the see, you have recordings, you have everything for that particular chapter. It's not there. For which particular chapter you let me? I mean, if you can tell me. I mean, for who? I mean, the subtopic for which you are not getting that particular study notes. So I need to check, because what happens sometimes there is a technical glitch. I'll let you know first. We are working on this. If there is a feedback of yours after each class, so if in any particular case that particular window is directly closed, okay, due to that particular timing and time bound, so the study note is not going to be created. So there is a technical glitch even after completing the class. So if you are not finding any particular for the whole chapter, so please let me know. If you are not finding a single or two class, or one or two or three class, or for any particular subtopic, so please let me know also. Clear, beta? Okay. So I am telling that magnetic field of a solenoid B equals to mu naught. B equals to mu naught Ni. And I hope and I believe you remember, everyone, how we derive that, where N is number of turns per unit length. So here beta L is a perimeter, because this particular length of solenoid, I mean this, if this is your solenoid, again I can draw that if this is your solenoid of length L, okay, if this is your solenoid of length L. So if I'm going to convert this particular length into this, which is a look like a circle, okay, this one. So nothing going to be changed. The manner we writing, that is going to be changed. Now this length, now my length is going to be converted as a perimeter. This is your perimeter, and your length is going to be circumference. Instead of circumference, you can say perimeter. And perimeter of a circle is nothing but 2 pi r. So that is why instead of writing small n, we can do that also, where I denote the amount of current passing through the solenoid, let r be the toroid's average radius, and n be the number of turns per unit length. Then n equals to 2 pi r n, capital N equals to 2 pi r n, and the toroid's average perimeter number of turns per unit length. As simple as that. Is this clear? So you can write this one also, or you can write this one also. B equals to mu naught Ni, where small n can be, not this color, a small n, again this, but here L is 2 pi r, because this is a toroid, circular in shape. So length can be perimeter, as simple as that. Clear everyone? We already discussed that much, in the previous class. Moving ahead, application of toroid. It is used in the creation of musical instrument. A toroid is used in the modern medical equipment. It is utilized in the telecommunication industry. Okay, nothing more we need to discuss about it. This is the main topic here, and after that we are going to do the thing. So the main thing here is we're going to find the force between two parallel currents, if they are having same current, if they are having opposite current. Maybe in this PPT or PDF they talk about only same current, but in that also I can teach you about opposite current also. First of all, you need to think, you need to understand, that is very very important. Note, whenever the current in the parallel wires flowing in the same direction, so they apply attractive force, because this particular question they ask generally, mainly, and in your vivas also, and then you're going to confuse, not you, but so many teachers also going to confuse. Even myself in the early period of timing, I'm going to confuse what is going to be. So, but after this particular class, you know, you are not going to confuse. So first of all, let's discuss the note, how it is going to be and why so. Why this happening. So note is first one. Um, hmm. Two current carrying wires, two current carrying wires, two current carrying wires, two current carrying wires, in which current flow, in which current flows in same direction, flows in same direction, apply in the same direction, the magnetic force they apply. This is not two current carrying wires, or I need to reframe this. Force between two parallel current carrying wires in same direction is attractive force, or you can say magnetic force. That is correct one. Magnetic force is attractive, that is good, short and subtle, attractive between two parallel current carrying, between two parallel current carrying wires when current flows in same direction. When current flows in same direction. What is the meaning of saying that? Same direction. Okay, let me write in the middle. Means this is your one wire, right? Okay, this is your one wire and this is your another wire. So when in both the wires, or in both the conductors, maybe the current flowing in the same direction, as you can see that I1, I2, so they are going to attract each other, as simple as that. Or the magnetic force between them, between two current carrying wires, is attractive. Or vice versa means in opposite sense, the magnetic force is repulsive when the direction of current is going to be opposite. Is this clear everyone? Or magnetic force is repulsive between two parallel current carrying wires when current flows in opposite direction. And that is very easy to understand. Once you understand, then you don't need to learn this. And then derivation is easy also in opposite direction. Okay. So let's discuss this for parallel wires, or you can say for same direction current, and then we are going to discuss for opposite direction current also. Is this clear? So very easy, very basic. As we know, magnetic field for a current carrying wire. Magnetic field for a current carrying wire. For a wire. I am just writing for a wire. Okay. So that is going to be, what it is going to be? V equals to mu naught I1 4 pi d final instead of this. Okay. 2 pi d. Okay, you can check it out in the previous classes. I already derived this. So that is magnetic field for a infinite wire, for a very long wire, or you can say for an infinite wire. That is going to be. Is this clear, everyone? So this is your magnetic field B1 due to this particular I1. Clear or not? Tell me. Is this clear till now? Just write, type yes or no if it is so. Is this clear, everyone? Okay. And we have one more formula from the previous classes already. That is force, or you can say magnetic force, is IBL sine theta. IBL sine theta. Or if I'm just writing in a vector form, so sine theta n. This is already clear to you guys. We already discussed this thing in the first classes, or you can say previous classes. Clear? So beta, when this particular wire have a current, okay, you can understand in this wire 1, when we apply a current in wire 1, so it creates a magnetic field. Or due to this particular magnetic field, you can understand in this way, due to this particular magnetic field, when this current carrying wire, second wire, is bring in this particular magnetic field, so that particular conductor or that particular wire is going to be attracted. As simple as that, due to this formula. This is your magnetic field, and that is your force in 2, or you can say force 1 2. Force 1 2 means force on 2 due to magnetic field of 1. I2 B1. L is the length of wire. Is this clear, everyone? I2 is the current due to this. B1 is the magnetic field due to the wire 1, and L is the length. As simple as that. Is this clear? Is this clear with everyone? Now the main thing arises the direction. If the just give me a minute. If the direction of magnetic field is going to be opposite here or here, so they're going to be attract. Opposite means what? One behave as a north pole, one behave as a south pole. Then they are going to attract. But if both the side behave as a south pole or north pole, so they are going to repel. Simple. That you know this thing simply. Is this clear? Means, okay, understand here first of all what happening here. Suppose this is your one magnet and this is your another magnet. I'm just going to remove in a minute. This is your north pole, this is your south pole. If I bring south pole here first, so what is going to be happen? They are going to attract each other. Clear? But if I am reversing this, Instead of south pole, if I'm creating a north pole, as simple as that. Now they are going to repel each other. Now they are going to repel each other, as simple as that. This is clear. In a same sense, if one, I mean the magnetic field is going to be inward in this particular periphery, or here it is going to be outward also. I mean this is your magnetic field out of the plane of paper, and this is also out of the plane of paper. So both are same poles, so they are going to repel each other. Clear? Or if the condition is going to be reverse also. Reverse means this is your magnetic field B inward, this is your magnetic field B inward. So then they are also going to repel each other. This is the sign of repel each other. Clear? But if this situation is going to be changed, one is, I mean the magnetic field due to wire 1 is going to be inward, or you can say outward, and the magnetic field due to wire 2, it is going to be inward. This is your outward, this is your inward. Now the pole is going to be changed. Inward we treat as a north pole, outward we treat as a south pole. There is a one thing. Why so? Because N anti-clockwise behaving as a north pole, or south as a clockwise, because it assume as a clockwise in this way. So it assume as a this south pole. Okay. So treating this analogy, north and south, or anti-clockwise, or you can say inward, or for clockwise, or outward. So treating this in mind, when the magnetic field for wire 1 and wire 2 is going to be reverse in direction, they are going to attract each other. When they are in same, so they are going to repel each other. This is clear, everyone? Because if this is not clear the direction wise, even if I teach you the formula or everything, that is not going to clear in your head. Is this clear, everyone? Clear, beta? Good. If it is clear, then nothing is going to be bother you now after this. Okay. So, okay. Once again, coming to this. Now you can see we have a wire 1 in which I apply the current, or this is going to be in this direction. Clear? So the magnetic field here due to this is going to be inward. The sign is going to be drawn here wrong. It is inward here and it is outward here. You can check with the help of right hand thumb rule. This is my wire. Okay, treat this, take your pen like this and treat it as a wire, and the current is going upward. So when the current is going upward, put your thumb in the upward direction. So the right hand side of the wire is behaving as a inward magnetic field because it is going in this way. Your four fingers going into this way, and the left hand side is going to be outward because your four fingers coming out. So this is your inward magnetic field, this is your outward magnetic field. This is your inward, this is your outward magnetic field. They are opposite in sense. That is why they are attracting each other. This is your B2. Instead of B2, this is B1. Okay, this is your B1, which is inward, and this is your B2, which is outward. So they are going to attract each other. As simple as that. Clear, everyone? Is this clear, beta? If I am going to reverse the direction, okay, just draw a small wires here. This is your one wire, this is your wire 2. Okay, let's change the color also. This is your wire 2. Okay, this is your wire 1, this is your wire 2. And if I am going to do this, now what you going to see, this is your inward also, or this is your inward also. Just do this thing. Instead of same direction, now your current is going to be in the downward direction. The moment your current is going to be in the downward direction, so the left hand side becomes inward or right hand side becomes outward. Is this clear, everyone? If you don't understand, do this with the pen. As simple as that. And remember the right hand thumb rule, nothing more. Okay, take your pen in this way. If the current is going upward, so the right hand, in the right hand side, your magnetic field is into the plane of paper, or inward, or right left hand side becomes outward. The moment you change the direction of a current in this way, now your left hand becomes, or left side, the magnetic field is going inward, or right side it is coming out. As simple as that. Clear? So the moment I reverse the direction of my current, as you can visualize here, so it is going to be same, and then they are going to repel each other. And that is what I written over here, first of all. Okay. So whenever this particular theoretical question or any particular type of question comes in front of you, the type of force, attractive or repulsive, between two parallel current carrying conductors or wires or anything. So attractive, repulsive, you need to understand this, and that is clearly mentioned here. Attractive, when current is flowing in the same direction in both the wires, attractive force is exerted. Repulsive, when the current flowing in the opposite direction in both the wires, the repulsive force is exerted. Why it is going to be, I clearly mentioned you. Now in the next slide we are going to define the amount of force, but in general these two formula we are going to consider. First formula is this one, and second formula is this one, nothing as such. We know that whenever there is an infinite or very long current carrying wire, so okay, on the next page there is a formula, mu naught I upon 4 pi d sin alpha by sin beta. Alpha beta becomes 90 degree. So sin 90, sin 90, 112, and 2 4 pi d, instead of 2 it becomes 2 pi d. Then we have a force formula. In any particular magnetic field, whenever any particular current carrying conductor is going into that particular magnetic field, so it experiences a magnetic force which is IBL sin theta. IBL, as simple as that. And it arises from QVV, nothing more. Clear, everyone? So due to this magnetic field, and this magnetic field is going into the current carrying presence, or you can say this particular current carrying wire coming into the magnetic field of influence of 1, so that is going to apply a force. Nothing as such going to be happen new here. But what is happening, due to current in wire 1, the magnetic field arises, and due to this magnetic field, when we you can say put that particular another current carrying conductor or wire in the presence of generated magnetic field due to current carrying wire 1, there is going to be attractive force, magnetic force, IBL sin theta. Clear? Clear? And that is your formula. So the magnitude of the field due to the first conductor can be calculated. Okay, can be calculated by using Ampere's law, BA, or you can say in wire 1, or instead of A, just give me a second. So suppose this is your wire 1, or you can say A, this is your wire 2, okay, and the distance between them is D. This is your distance between them is D. So this is your wire 1, current I1, and okay, let me write in a proper way, I1, I2. So this is your magnetic field for a wire is B equals to mu naught I upon 4 pi D, or A, or sine alpha plus sine beta. For infinite wire, what we say, for long wires or infinite wire, what is the meaning of long wire or infinite wire? Can anyone tell me? Sir, kindly excuse me for a minute. Yeah, why not? I'm asking what is the meaning of long wire or infinite wire? When we can take this particular condition? This is your general formula. Can anyone tell me? When we can shift this particular formula into this formula number 1. Anyone? Okay, so this is your magnetic field due to wire A, and this is your wire B. So the force on a segment of length of wire 2 due to wire 1 can be, or you can say 1 or 2 also, F21 I2LB1. Okay, I2 is I2, L is length of this particular wire, or B1 is, we already, mu naught I1 2 pi D. So when we put everything into this, so that is your attractive force. Is this clear? Is this clear with everyone? Okay. Still on my this particular question, like where we going to convert this particular general formula of A, or you can say magnetic field due to a wire, into this formula number 1. At what assumption, at what conditions we are going to say a long wire? How much long? 500 meter, 200 meter, 2 meter, 3 meter. What is long? Tell me anyone. How you can understand this? How you can digest this formula? It is going to be long for me. It is not going to be long for any particular practical application or any particular sense. So how we can say that that is long wire or infinite wire? Did you know this? Basic question. Very. And if you don't know, so then why don't you ask? This is also the question. If you know the conditions, when I'm going to say my wire is long, so please tell me. And if you don't know, then why don't you ask? That is question also. Tell me anyone. See, in humans also, someone is 5'6", someone is 5'6", someone is 5'7", 5'8", someone is 6.1, 6.2, someone is 7 point something also, right? So there is an average height of each particular state, each particular country. So on the basis of that, we can say small wire. When a small part DL is taken, comparing the DL, the length of the wire is infinite. No, beta, no. Suppose, okay, for your answer, I am about to reply this. This is your wire of length L. I took this much DL. So is this infinite wire? No. Isn't it? Is this taken as an infinite wire? No, because it have a length L, na? So if something have a length L, so how can I say that is infinite wire or long wire? What if this length is going to be 2 meter only and that DL is going to be 0.2 centimeter? Okay, so you don't know. The very basic thing is when radius, okay, when the ratio of radius to the length is going to be very, very less as compared to 1. And in most of the cases, that is going to be. Even for 1 meter length, we're going to say, we're going to assume that that is a long wire. As simple as that. Clear? Because the radius is going to be in mm or in centimeter. Or if the length is going to be few meters, we can say 50 or 100. So then we consider that particular length is a long wire. Clear, everyone? Because then the ratio is going to be very, very less this one. Suppose my radius is 2 centimeter and my length is 100 meter. Okay. Now see the ratio 0.02 or 0.2. Okay. And then that is 100. So it is very, very less as compared to 1. So keep this in mind. This is the condition to see or to check long wire. Because okay, one important thing I want to tell you here on behalf of that, in physics, the infinite is nothing as such. Everything can be finite, or infinite is finite for something and finite is infinite for something. You are going to say, sir, is going to be the jumble word key something. Sometimes I'm saying infinite, sometimes I'm saying infinite. So what I'm saying, I'm repeat my sentence, I'm repeat my words. In physics, we can define infinite because infinite can be defined or infinite can be changed. Very basic manner. If you put an ant or an elephant alongside, or you can say in one presence or in one area, so the area covered by the foot only of the this particular elephant is going to be infinitely large or very large or infinite as compared to the ant. Clear? But if you're going to place that particular I mean, if you're going to change that scenario, and now the situation is elephant in front of whale, so that is going to be drastically reversed. Okay, did you understand what I'm saying? One basic example, 30 seconds as compared to your living life, you can say 60 years. So now this 30 second is going to treat as a very infinitely short duration, or you can say this 60 years is going to treat as a infinite time as compared to this range. Clear na? But if I'm talking the, you can say very I mean few phenomenon which is going to happen in a within a fraction of second. For example, the glowing of a bulb. The moment you click or the switch on that particular button, that particular electric bulb, electric fan is going to turn on. Clear? So then you cannot say that 30 second is going to be infinitely small either, or that 30 second is going to be infinitely large either. So that is the way in which we, you can say, treat infinite, or you cannot treat define infinite in physics. So in physics there is no such word like infinite is something which is not defined. We define infinite, at least in physics. Clear everyone? Okay. So this is very simple formula, and on the basis of that, okay, now this is the force between two parallel current carrying conductors. Similarly, we can calculate the force between two wires between exerted by wire 2 on 1. What I'm doing? Okay, so this is your formula or force, which is F21, force on wire 2 due to 1, and this is F12, force on wire 1 due to 2. As simple as that. Instead of finding magnetic field for first wire first, I'm finding the magnetic. So many examples what I'm talking right now. This is your I1, this is your I2. So right now I'm finding B2 first, and B2 is nothing but mu naught I2 2 pi d. Okay, and then F12 is nothing but IBL, which is I1 B2L. So that is going to be F12 mu naught I1 I2 divided by 2 pi d, and there is something L also. Okay, length of wire L. So that is A wire, that is B wire, you can read that. And obviously, if this particular, if on this particular wire, or you can say if this particular wire attracts this particular wire in this direction, so this wire is attract this particular force in this direction. So we can vectorially represent this one also. F12 is nothing but minus of F21, or when we take a mode or magnitude wise, we can do this also. Is this clear? Okay. So this is very important formula first of all, and this confusing too a little bit. This one also, or this page also. Okay. Is this clear, everyone? If you have any question, doubt, anything, so you can ask me right now. Because after that, we just going to reframe more in number of words or in number of sentences. Nothing more we are going to do as a concept wise. So the next thing is force between two parallel current carrying sheets. So consider two. Now instead of wire, we have a sheet, and we treat as the same sheet carrying a magnetic field of reduction B between the planes. Outside the space, there is no magnetic field. The magnetic force acting per unit area of each plane is F equals to B square 2 mu naught, and that is not correct formula. F equals to B square upon 2 mu naught. And how we can find this? Okay, this is how we can find this. the magnetic field due to one of the sheet is half of the magnetic field, the force on the uh, wait, I into length into breadth. Okay, simple as that. What they can say, instead of, as we know there is a wire. Okay, the wire have a magnetic field B. What is the formula? I mean, we know that. Instead of wire, we have now this kind of sheet. Okay, just wait for a while. Now this kind of sheet. And there is a similar, just wait for a while. There is a similar sheet in this way also. Okay. So we have a two wires. Making two wires, we can make one sheet. And this is sheet 2. So whatever the magnetic field due to one of the sheet is half of the net magnetic field. But as simple as that. Clear? Because whatever the wire we are going to pick, the magnetic field B. So for whole sheet, it is going to be 2B. For one sheet, we are going to take half only. The force on the sheet is given by F, which is 1 by 2 into B, then I, and simply length into breadth. Because now we have a breadth also. Or you can say we have this. This is your D, and that is your length. So that is going to be mu naught square. I mean force B square upon 2 mu naught per unit area. Nothing more we are going to discuss about. Is this clear? And this is, they don't ask much about this. Okay. So the next thing is your this. Okay, try this one. This is very easy. Two straight infinitely long and thin parallel wires are spaced this much apart and carrying current of this much. The magnetic field at a point distance 0.1 meter from both the wires when currents are in same direction. So tell me how much current is going to be applied. Tell me which particular is the correct answer. Then we are going to discuss a little bit more. Tell me which one is the correct answer, beta. A, B, C, D. 0, it is going to be C, is going to be A, is going to be B. See, the main thing is going to be, obviously, that particular formula what we already discussed, but more than that, the direction and the net magnetic field, or you can say the net magnetic force. D. Wow. Why 0, beta? Explain your answer also, whatever the particular option you choose. Anyone? Okay. See, the main thing is two straight infinitely long and thin parallel wires are separated, are spaced between it. So, from the moment you hear this thing, this is your wire 1, this is your wire 2, as simple as that. And carrying a current of 10 ampere each. So this is your 10 ampere. And this one is also 10 ampere. The magnetic field at a point distance 0.1 from both the wires. Okay. So now you need to find the magnetic field at a point distance 0.1 meter from both the wires. From both the wires, the net magnetic field you need to find. So obviously the net magnetic field is going to be opposite. Here it is going to be inward. Here it is going to be outward. Clear na? Is this clear till now? I am not repeating anything. This is going to be inward, this is going to be outward. So obviously the net magnetic field is going to be, you can say, something which is going to be added down, because both the magnetic field in opposite direction. So we need to add. So what is the add or direction? That is the main thing. So point P is situated at an equidistance from A and B. Hence, for the given case, the magnitude of the magnetic field at P due to both the wires will be same. B A equals to B equals to B mu naught I upon 2 pi D. Put this everything and get the field first. This is your magnetic field B. Due to 1 equals to due to 2 equals to 2 into 10 to the power minus 5 Tesla. Nothing more than that. Just putting the values. Clear? Clear na? And if someone is thinking how this mu naught I upon 2 pi D convert into 2 into 10 to the power minus 7 into 10 upon 0.1. So beta mu naught equals to 4 pi into 10 to the power minus 7. So this 4 pi, 2 pi cancel each other, and then we have this formula. Okay, if someone is thinking in this way also. So we get this first. Now, if the wires carry current in the same direction, so B and B, I mean both the magnetic field B1, B2 are in opposite direction. Will we have the direction as shown in figure? They are not shown in figure, but okay, yeah, I draw that personally. So this is your going to be, if it is going to be outward, so it is going to be inward. Now the net magnetic field B is resultant and total 2B cos 30 degree minus I. Why it is going to be? Now you tell. Why it is in negative direction? Okay, how it is going to be from here? See, one magnetic field is going into the plane of paper. You can say negative Z. When it is coming out of the plane of paper. So try to understand this. One is going inward, one is going outward. The net summation is going to be in the 30 angle degree. Okay. Suppose this is your Z direction. One it is going in this way. One magnetic field is coming in this way, another magnetic field is coming in this way, and suppose this is your Z direction. Clear? So if I need to edit this two vectors, because magnetic field is a vector, so how can I do that? As simple as that. This particular vector have a two component, then sine component and cos component, and the net sum, because sine component is going to be here, which is going to be totally opposite. It is, yeah, in this way you can understand. This is your one magnetic field, this is your another magnetic field. This is B1, this is B2. Now B1 and B2 both have this and this, this and this. So this is your wait, one thing I draw wrong. This and this. Now this. So this B1 sine component and this B2 sine component are opposite, so they cancel each other. But they are in same direction with the negative sense, so they are added down. Clear? Is this clear, everyone? This is the scenario. This is happening here. So that is why we took B R equals to 2B cos 30 degree minus of I, and then putting the value of B and cos 30 degree. As simple as that, you get the result, and the result is A. Correct option is A. Is this clear, everyone? This one you need to understand. Because from this particular diagram you can understand this is going in this direction, this is going in this direction. So this is your, if I just took theta equals to 30 degrees, so this is b1 cos theta and that is b2 cos theta, and cos theta here is 30 degrees. Clear now? And how you can assume that, how you can say that that is correct thing. One more thing. As you can see, this one and then this one. Okay. So beta, just a minute. This is your x, this is your y, not your x. But this is the x direction, this is y direction, this is z. So for x direction, you can see that for this negative x direction, you can automatically see that that is going to be either 45 or either 30 degrees. It is 30 and it is 60. A little bit easier to understand. Clear na? Automatically means this y is, this z direction is perpendicular to both, but for negative x it is going to be this 30 and 60 degrees. So from that we can do this. Okay, this is your next one. Two current carrying wires of equal length are parallel to one another and spaced this much apart, producing a force of 1.5 into 10. Okay, the force is, this is typo beta, sorry for that. This is your force. Okay. Per unit length. What will be the force per unit length on the wire if the current in both the wires is doubled and the distance between the wires is half? As simple as that, you need to find a relation. Hint I am going to give. What is hint? Very simple. Hint. Okay, this particular formula is per unit length also. F12 by L. This particular formula na, mu naught I1 I2 upon 2 pi d. This is your per unit length. Why so? Because simply we know force is I2 B1 L. If I'm talking for this particular only, you can say 2 on 1. Okay. So the moment I do the per unit length, so length is going to be divided and then this formula is going to be. If it is not a per unit length force, so length is going to be multiplied also here. But I already say per unit length, so then this force is going to be. Everything is given. This is your case number 1, case first. Okay. In case when d equals to 4.8 meter apart. So this is your force. Just find I1, I2, nothing more. Then product. What they said, if the current in both the wires is doubled, so I1, I2 becomes 4 times and the distance between the wire is halved. So that is going to be 8 times. So just simply put and then find f prime in terms of f and do the, there is going to be some constant and tell me the answer. Okay, there is going to be some constant and tell me the number. Clear? Because we know force per unit length of in two parallel current carrying conductors or wires is this. If I change the value of I1, I2 and I change the value of D, so I can find this new force or updated force F prime in terms of old force. That we need to do. Is this clear, everyone? This is clear na? Hari May. Okay. Why are you looking so sleepy today? What were you doing in the last night? I mean, sorry to ask this personal question here. Is this okay, everything? You look sad too. It's okay, beta. Tired. Yeah, I can see that. I mean, I'm just going to say this word also. Okay, so do that and tell me the answer. I'm tired too, little bit. Or okay, do one thing. After this, I think we have torque. Yeah. Okay. So after this, we have a torque, or which is a new learning concept. So took a break and do the question in the break time. And then in one go, we going to understand the whole concept of torque and everything. Because then I'm not going to give you. Okay. So force in two parallel current carrying wires in opposite when the current is flowing in opposite direction, they are going to repel each other. When the force is going to same direction, I mean when the current is going to the same direction, they are going to attract each other. And that these kind of simple formulas and simple numerical problem you are going to face. Next thing is going to be a little bit not difficult, but sometimes they ask a complex question from that particular subtopic, which is torque in a current carrying coil or in a current carrying wire, which is going to be placed or situated in uniform magnetic field. As simple as that. Clear? So we are going to do that after a break. Meanwhile, you can solve this. Find this relation first. Find this relation first, and then force. Yeah, force per unit length. Okay. Hello, hello, hello. Am I audible? Hello, hello. Audible, sir. Okay, so tell me what is the answer or how much this particular relation is comes first of all. This one, f prime equals to how much of f? Tell me, beta, anyone? But turn your cameras also. Everyone. If I'm saying turn on your camera, why you turn on your camera? Okay, sir. Anyone? How much is this relation? Tell me, beta. Okay, so as we know, I already discussed this thing. FAB equals to mu naught IB by 2 pi d per unit length. If I prime A, if I prime A equals to 2IA, I prime B equals to 2IB, and D prime equals to D by 2. So 2 into 2, 4, 4 into 2, 8. Why 2? In this page you can see that. So 8 times of F, nothing more than that. And just you need to multiply 8 into 1.5 and that is your correct answer. Even in this you don't need to take 1 minute. Why so? You just need to write in this way F equals to force per unit as mu naught I1, I2, or you can say IA, IB upon 2 pi d. So F directly proportional IA, IB divided by D, because I don't need to do this and this. I mean anything with this and this. Okay, this and this. So I prime A becomes 2IA, then I prime B becomes 2IB, and then D prime becomes D by 2. Put into this formula 1 and you get simple F prime is nothing but A. 2 into 2 into 2, and then put into the values. Is this clear, everyone? Clear? You don't need to put values every time. As simple as that. I don't know how many times I need to discuss this. Okay, so there is a torque on a rectangular current loop. See, as we have when we put any particular loop, or you can say magnetic dipole, not magnetic. We put electric dipole in this particular uniform electric field. So this particular dipole treated, or you can say the dipole feel that particular torque. Why so? Okay, first understand this, what is happening, and then, I mean what I'm telling to you guys, and then we discuss. Suppose this is your electric field, because when you make that analogy, so you understand better. And in this particular electric field, we have a formula. When I put this, wait, when I put a dipole, this is your dipole. Okay, this is your dipole of two opposite charges, Q and minus Q, and this length 2L. So this dipole, I mean that particular dipole, on that particular dipole we face a rotational force, and rotational force is nothing but R cross F. As simple as that. Is this clear? Okay, or this R cross F in simply P cross E, or you can say P cross E if I'm not wrong here. P is dipole moment, and electric dipole moment, electric dipole moment 2QL, and E is electric field. This is also, so torque is nothing but tau is nothing but P cross E. And from where, how we get this formula? As simple as that. Because these are opposite and when you apply the force, so the force on this particular charge is going to be in this way, on this particular charge is going to be in this way. So the net force is going to be 0, but this particular dipole is going to rotate in this way. Yeah. And when we do that, when we put into this general formula of torque, we get this relation, as simple as that. Clear first of all? Now what I'm saying, now what I'm saying, instead of thinking or instead of treating electric dipole, if I put a current carrying wire, okay, if I put a current carrying wire, this is your current carrying wire, or this is your uniform magnetic field B. And we already know this thing, this is your current uniform magnetic field B, or we know this particular current carrying wire or current carrying conductor treated or behave as a magnet or a temporary magnet. The moment until unless current is going to be flow, this is treated as a magnet. Here the magnetic field is going into the plane of paper, or here it is going to be out. Clear? So this behave as a north pole, this behave as a south pole. As simple as that. So the same scenario is going to be, now we have a two dipoles here of this particular magnet, or you can say due to this wire, the magnetic field create, and we have a magnet. We have a two dipoles, as simple as that. North pole and south pole. Simple. Two dipoles created with the monopole. So in a same sense, when I put my current carrying wire, which is treated as a dipole, or you can say magnet, that particular magnet feels or trying to rotate, or you can say going to rotate, not trying to rotate, but going to rotate, and that rotational force is known as a torque. As simple as that. Why should I tell you this one first? Because it is so analogous, or the combination, the numerical problem they can make on the combination of both. Clear everyone? Is this clear everyone, beta? Tell me. Because if you understand this, everything other than this, just the formulation in a same way, nothing more. Is this clear everyone? Please let me know. Everyone means everyone. Okay. Now for the same case, instead of wire, you can treat it as this. Instead of wire, we can treat this your rectangular loop, or this rectangular loop is going to rotate in this way. Suppose this is your going to be axis. So on the for this particular axis, this rectangular loop is going to rotate in this way, in a uniform magnetic field. Nothing more is going to be. Okay. Clear? Fair enough? Because okay, why it is going to be very simple again? Because if it is a current carrying wire, so here we have magnetic field, here we have current in this way, here we have current in this way. So they are going to repel each other, first of all. And when they are going to repel each other, so the net force is going to be 0, or this coil is treated, this coil is, instead of getting a net force, that is going to be rotated in a uniform magnetic field. That we're going to find on the next slides. So consider a case where the rectangular loop in the same plane as the magnetic field B, the loop's arms that are parallel to the magnets receive no force from the field, but the arms that are perpendicular to the magnets receive a equal force, or force equal to F1. Okay. And now you can ask me this, the arm or this current, why we cannot feel, or why we cannot talk about the force on these current, or you can say if it is A, B, C, D, and my my magnetic field is going in this way, why I am not talking about the force on A, B or C, D? Tell me anyone. Now you tell me this thing. Why this sentence, the loop's arms that are parallel to magnet or magnetic field? Suppose this is your magnet or magnetic field. So why we cannot have force on AB or CD, or I am saying this, I am asking this, FAB equals to FCD equals to 0. Why so? Tell me anyone. Why I take this force as a 0? And we are not talking about these forces. Tell me beta anyone. This is very easy. Even I write that particular formula in the previous slides also. Just think a little bit and then the answer in front of you. Tell me why this force is going to be 0. Easy one. If it is not getting in your head, then that is so problematic. Why should I talk about only force on BC and AD, or you can say AD and CB, not AB and BC? My question is this: why? Anyone? Very basic formula. That's why I'm saying keep your eyes and mind open to it. More than your eyes, mind. F equals to IBL sine theta. Clear? So here theta is 0 degree and sine 0 is 0. What is theta here? The theta here is the uh, angle between current carrying, or you can say angle between length element L. This is your length, vector length, and this is your magnetic field. So this is my vector length, or you can say this and this. So the angle here is 0 degree or anti-parallel, 180 degree. Clear? Because my force is IBL sine theta. Force is a vector. So if I'm writing somewhere IBL only, so that is doesn't mean it is that much only. That is the magnitude of force. Clear now everyone? F force is I L cross B. That is the sense. L cross B gives me IBL sine theta, and that theta is going to be 0 degree for parallel wires, or you can say for parallel magnet, or the length element which is going to be parallel for magnetic field. You can treat any particular sentence, but the result or the answer is same for everyone. Clear this one? So then F1 equals to IBB. Now what is B here? In the next page I'm going to see, I'm going to tell you, but B is nothing but length or breadth. Instead of length L, we can write breadth. If I talk about this particular loop, so here you can understand this is your length L, so this is your breadth B. So obviously I get my force IBB, because on length the force is going to be 0. Clear? And this length element is perpendicular, so that's why I can write this. If this length element is tilted a little bit, so then I need to write theta also. But you can see this length element, I take this particular as a length element, and this is my magnetic field. So that is going to be theta equals to 90 degree here. Okay. So that is why I directly write IBB. This force is directed into the plane's direction. In the same way, we may write the formulas for a force F2 applied on CD. On the next page, they can give you the formula. So torque on a current carrying loop F2 IBB equals to F1. The loop's torque is given by the loop's net force is 0. As we know, net force is 0 because once it's going in one direction, another is going in the opposite direction. So F net is nothing but F1 I, you can remember this, plus F, I mean not remember, understand in this way, where F1 equals to F2 equals to IBB. One is in the positive x direction, one is in the negative x direction. So F net is 0 in this way. But torque tau equals to F1 A by 2, F2 A by 2, and then A by 2, A by 2 gives me A. What is the meaning of this A by 2? Okay, I can draw here. clear page and then you can understand. Suppose this is your magnetic field. In this particular magnetic field B, we have this loop, not this much, this one. So this is my A, B, C, D. So on this my force is going to be 0. If okay, one thing I draw wrong then. Yeah, now this is perfect. So if this particular length is A and this particular length is B, so only I have force on A and B. Okay, I need to change color also. For this is your A, this is your B, and obviously that particular coil is going to rotate in this way. So automatically the force, or you can say automatically this perpendicular length for this force, this perpendicular length is not this color. Which color I take now? This one. This is your going to be A by 2. Or this is your going to be A by 2. Clear? If this is your whole A. This is your A by 2. Just give me a minute. And this one beta is your A. The whole length, and this one is B. Clear everyone? So net force is 0 due to this, but torque tau equals to F1 A by 2 plus F2 A by 2. Net torque means total torque. IBB A by 2, IBB A by 2, A by 2, A by 2 becomes A. So IAB A. And what is the meaning of this? A or B, this is area of rectangular loop, or the area of rectangle, area of a rectangular loop, which is A. Clear? So that is your torque, IAB. Here capital A is, this is your magnitude. Here capital A is, or obviously that is going to be treated as a vector also, because B here is vector. So torque tau equals to IAB. The area of the rectangle is AB. The loop rotates in anti-clockwise manner due to this torque. What is the meaning of anti-clockwise here? This loop is going to rotate in this way. Okay, or from this particular end in this way. Like your loop is going to rotate anti-clockwise in this way. Is this clear, everyone? Clear na? This is very easy. Clear? And 2 times I draw this, so I think now this is very easy. Clear, everyone? Everyone means everyone. Just type yes, everyone, if it is clear. So, or if you need any particular thing to more explanation, let me know. But I don't think you need any more after this. Okay, so this is your torque on a rectangular current loop. As simple as that. Okay, moving ahead, torque on a rectangular current loop, this is going to be done. Okay, this is okay. Now in this particular, what they said, if that particular loop is not perpendicular, it is given to any particular theta. Means consider the situation, instead of perpendicular thing, consider the situation where the plane of the loop is not parallel. Like this plane, or this particular is not situated in this way, but it is have some angle. This loop having some angle with this magnetic field B. Okay, this is your magnetic field B. This is your magnetic field B, or uniform magnetic field B. So then what it is going to be? Parallel to the magnetic field, let be the angle generated by the field, and let be the coil's normal. Coil's normal means perpendicular to the coil is theta. The forces acting on the arms BC and DA will always be in equivalent size and always act in opposite direction, as can be seen. The forces on arms AB and CD are determined by F1, F2. These forces sorry, are in similar size and direction can be produced by F1, F2, IBB. But here we need to take care of this theta also. What I am repeating again, just give me a minute. Now suppose this is your magnetic field. Just give me a moment, I can draw in a proper. Okay, this is your magnetic field. Instead of parallel plane, what is the meaning of parallel plane? That particular coil is going to be equally. Okay, now your coil is tilted in this way. Instead of parallel plane, now coil have some angle theta. What is the meaning of saying that this particular normal? Okay, just give me a second. This is your normal. Okay, now this particular normal, you can see that exactly. Now this particular normal have some angle theta. Clear? I mean, what is the normal again? If I need to draw this particular axis, so this is my axis. So this is going to be this. This is going to be your axis, and due to this particular axis, that is my going to be theta. Clear? So instead, I mean everything is going to be repeated the same. This F1 equals to F2 equals to IBB. Clear? Now this is your B. This is perpendicular. I mean we take perpendicular. But or even if we take here sine theta component, sine theta, so theta is going to be same. So net force is going to be 0. But when we talk about this particular thing, which is, you can say, torque. So for torque, instead of directly A by 2, now we take A by 2 sine theta component only. This is your in the direction. So this one is A by 2 sine theta component. This is your A by 2, and A by 2 sine theta component you need to take care because of this angle tilted. So torque tau equals to F1 A by 2 sine theta. Similarly F2 A by 2 sine theta and IAB sine theta. So again here, instead of normal thing, torque tau becomes IAB sine theta. Here this particular theta gives the direction of torque. In the previous case, we get the direction of torque on behalf of magnetic field. Clear? Theta tells us the direction of torque. And again, this particular loop is also rotating in this way, anti-clockwise, north to south. Clear? Clear now, everyone? Okay. Is this clear, everyone? Good. This is the concept. I mean, I already do that, but that is in diagrammatically, or torque on a rectangular current loop equation in vector form. So vector form is nothing, you can say, going to be changes. Consider a rectangular coil PQRS hanging in an induction field, magnetic field B with a uniform magnetic field. That you can see, that is a magnetic field, or you can say uniform magnetic field B. Okay. So let PQRS equals to L length PQRS, where PQ and RS is length L, and then QR and SP. This QR and SP is going to be taken as a dress B. So torque equals to tau IAB sine theta. So if instead of one loop we have n number of turns for that particular loop, okay, instead of one this particular current carrying you can say frame, in this particular frame we have n number of loops. We rotate our wire n number times. So that is the formula is going to be nothing Clear everyone? Moving ahead. In vector form NI A cross B. Here we take area as a vector. And A cross B because this is very easy to understand. NI A B. Okay, and sine theta. So beta sine theta is the angle between this area vector and magnetic field. So instead of this, I can write NI because these are the A cross B. As simple as this. Here A is area vector. And I hope and I believe you know this, what is the area vector. Area vector is nothing for any particular area. If we have a normal or any particular angle theta, so that particular normal is taken as an area vector, as simple as that. So the direction of torque, as I already discussed this thing, the direction of that particular torque is given by this sine theta. So instead of sine theta, for vectorially, for vector sense, we can write this. Torque tau equals to NI A cross B, and A cross B gives me the direction of this, gives us the direction of torque. The direction of torque. Is this clear, everyone? Just type yes if it is clear, so I can move ahead a little bit more quickly. Clear, everyone? Which one, beta? See, till now you understand? Yajira. NIAB sine theta. So instead of this, I can write this A cross B. But now I treat my A area as a vector. What is the meaning of saying that? Just give me a minute. See, this is the area of this. Okay. This is the area of this particular loop. Clear? And this normal vector, this particular thing is known as a direction of area vector. I mean, in this kind of scenario, we take as area as a vector. Why so? Because area behaving as a vector to give this particular quantity as a vector quantity in cross product. Because this n is number only, right? And I is a scalar thing. So what is vector other than B? We treat A. And what is the direction of this particular area? Suppose this palm is my area. I mean, this palm, it is that particular area which is having length and breadth. So this is area vector, or this is area vector, depending upon which, if I tilt my palm or if I don't tilt my palm. Yes. If I don't, suppose the magnetic field B is going parallel in this way. So this is my area vector, automatically perpendicular. But if I tilt this in this way, so this is going to be tilt also. I mean, this vector is going to be same, but the direction due to tilting this magnetic field either, or due to tilting this coil either. So normal is going to be changed, and when the normal of that particular area is going to be changed, so we say that that particular area is not a simple area, but it is the area vector. Okay. Special cases, nothing but I mean theta values put 0 and so. So torque on a rectangular current loop equation in vector form. Special case, first case, theta equals to 0 degree and cos NIAB cos theta. That is wrong. If it is A cross B, so it is going to be sine theta. Wait. Okay. That is NIAB. Wrongly written. Let me check. Okay. Then. So if we have a theta 90 degree instead of 0 degree, okay, 90 degree. So instead of cos, then we're going to write down sine, and then we have a sine theta. Here I need to sine theta, and here I need to put sine 90 degree, and then this is going to be correct. Is this clear, everyone? That is very easy. It's not even to tell every time. Like as we know, torque tau equals to NIAV sine theta. So we have two cases for that. Okay. First one is this. When theta equals to 90 degrees, so we have a maximum value. And when theta equals to 90 degrees, so when theta equals to 0 degree here, then we have a minimum case. 0 degree, and then it is going to be sine 0 degree equals to 0. Here we put sine, here we put 0. Nothing more than that. Okay, wait. But here in this formula we have sine theta, and when sine 0 degree is going to be 0, so torque becomes that. Clear, everyone? Okay, so that these are the simple cases. Okay, so this is your numerical on this. A current loop of area 0.1 and carrying a current of this held perpendicular to a magnetic field of intensity this. The torque acting on this. Everything is given to you guys. You just need to put into the formula and tell me the answer. Just do that quickly. Loop area is given, current is given, torque and theta is 90 degrees perpendicular to a magnetic field of intensity. Okay, so tell me which one is the correct. So do it quickly because then we have a one more important thing and then important questions too. Okay. So D. Everyone got D? Yes, beta D is correct. Simply okay. First of all, D is correct. Torque tau equals to what it is? NIAB sine theta. Here n equals to 1. They don't talk about the number. I is given, A is given, B is given, and theta is 90 degrees. So you just do IAB. Okay. More. Okay. On the next page, I can teach you this. Magnetic moment in the previous classes is IA, or you can say I cross A. Their area is vector, not I. As we know, M. As we have a dipole moment. Okay. So in this way, as we have a dipole moment P equals to 2QL length. In the same way, due to this current, in any particular area, we have a magnetic moment which is I cross A. Clear? So I can put this one also, and you can use this formula also. Torque tau equals to M cross B, because or you just simply instead of I cross A, this is simple multiplication, but it seems like a vector thing. So you do this I A. So when I put this torque tau equals to I A cross B, clear? So I can do that M cross B, as simple as that. And that is famous relation also, in the coming slide, we're going to talk about this. Clear? So putting this and then we get the clear everyone. This you can take it down as a series M. M is what? Magnetic moment. This is important. Okay, that is we need to discuss in the next. Okay, this one is the torque of magnitude is this experienced by a short bar magnet with its axis at 30 degree and a uniform external magnetic field V. How large is the magnet? As simple, how large is magnetic moment? So that is very easy again. Solution or hint. I'm not going to solve, but hint. As we know, torque tau equals to m cross b, and you can say m b sine theta. Everything is given now. Torque is given. Okay. Then theta is given. Then magnetic field is given. You need to just tell magnetic moment. So given that this is this, and magnetic moment is this. Okay. Is this clear, everyone? Okay. So you can put into the formulas and get the solution after the class. I mean, recheck this. So now this is very important. Magnetic dipole and magnetic dipole moment. We already did this one, what it is, but let's revise for next slide. That is important. So the magnetic dipole moment is defined as the maximum amount of torque caused by a magnetic force on a dipole that arises per unit value, or you can say per unit volume of the surrounding, per unit value of the surrounding magnetic field in a vacuum. It is a vector quantity and its direction is from north pole to south pole. Its SI unit is ampere per meter square and its series unit is erg per Gauss. Now I am again, here torque tau equals to m cross b. Okay, so what we are assigning this, m is a magnetic moment, that is torque on magnetic field. Clear? So what we can say that the magnetic moment is defined as the maximum amount of torque caused by the magnetic force on a dipole. As simple as that. Suppose this is your magnet, or you can say this is your dipole, north and south. So in this, I reverse this thing because then you understand it in a better way, north and south. So here the direction of your magnetic moment, which is M, is from north to south. Now this is your magnetic moment. Clear? So in simple way, magnetic moment is nothing but the maximum torque applied by any particular magnetic dipole or a magnet in the presence of any external magnetic field, or you simply write it down, the ratio of the maximum torque applied by this magnetic dipoles in presence of magnetic fields is known as a magnetic moment. So the torque applied on can be written as torque tau m cross b, where torque is the T is the torque acting on a dipole, M is the magnetic moment, B is the outside magnetic field. This is important. B is outside magnetic field. Clear, everyone? Is this clear, beta? Okay. Now moving ahead, this is important. As we know, current carrying loops or current carrying wire behave as a magnet. So simple, instead of writing M as a magnetic moment, we can write mu. This is your magnetic moment also. I think I already discussed this thing in the previous any classes, but still let's do that magnetic moment. Okay. So as we know, simple magnetic moment is nothing but I, A, or you can say I cross A. So for loop also we have, current carrying loop we have mu, which is NIU. N here, beta, is nothing as such but the number of turns per unit length, or you can say number of turns for a loop. As we can see, there are 1, 2, 3, or 1, 2, 3 loops we have. Is this clear, everyone? So current loop as a magnetic dipole, and we know that current loop behaving as a magnetic dipole, and magnetic dipole moment we are going to derive. We already derived in the previous classes, but still, and its dipole moment. So as we know, mu equals to NIA, where N is number of turns on the loop or in the loop, I is the current, A is the area inside the loop, and then okay, simply where it comes NIA, because this is your current carrying loop. This one, okay, and again this one, again this one. So suppose almost at the average radius of each particular loop have R. This is your radius R. So we know this magnetic moment mu equals to, sorry, NIA. So just putting the value of A, area, pi R square. That is your magnetic moment. Nothing I'm going to do, nothing I'm doing here new. The circular current loop acts as a magnetic field due to the current moving, due to the current moving in a circular direction or in a loop as its direction is determined according to the Right-hand rule. The circular loop acts as a magnetic dipole as a magnetic field is generated due to the flow of charges. Hence, the formula for a circular current loop is magnetic moment mu equals to Ni, and again Ni pi I R square, where I is N is number of turns, I is current flowing in the loop, and R is the radius of the loop. I don't think like any particular student have any particular query till this now, or do you have till this page, for this page? So let me know. Is this clear, everyone? Right? This is basic thing. I'm just putting the values again and again in the formula. Everyone, just type everyone instead of this Parikshit and Yajira again and again. Everyone, is this clear or not? Whatever I'm saying since last 30 minutes or 20 minutes. Clear? Good. Okay. So now we are going to find the magnetic field, or you can say we know the magnetic field. There is a axis and there is a long formula, so the derivation is not necessary. But sometimes in a reverse way, in this analogy, they can find. So there is a quick recap how to find magnetic field, or you can say what is the magnetic field instead of how to find what is the magnetic field for a current carrying loop as a magnetic dipole. Clear, everyone? So this is a current loop as a magnetic dipole, or you can say as a magnet. So consider a circular loop with radius R on the table, as you can see that, which is carrying a current I in an anti-clockwise direction, as it is also clear. Okay. Now take a point P. This is your point P. They don't put the name. That is L distance apart from the center. As you can see, that is L distance apart from the center. This is L of the loop. Therefore, the magnetic field B at a point P is given by C. I can derive this formula also, but that is going to be time taken. I give you just one simple way to find that. Whenever you have any particular, okay, in this way you can understand more. This is your current carrying loop of radius R. And if I need to find the magnetic field for this on this axis, x-axis, which is, you can say, L distance away from that. So what we're going to say, suppose now anti-clockwise current is going to be, so we treat this particular point, okay, just give me a minute, here and from here, okay, so simply that is going to be mu naught I upon, you can say mu naught I upon 2 pi d, but that is not going to be because it is a circular loop. For circular loop, what is the formula for magnetic field? If I am not wrong, mu naught I upon 2 pi r. Okay, but this r is not the simple one. Here r cos theta something, and this cos theta. Okay, is going to be r square plus l square to the power 1 by 2, and this r is r square plus l square. Okay, what is the meaning whatever I'm saying? This is your r, this is your capital area. Wait. Automatically. This is your r. So now you can see that using pt here, this is your theta 1, this is your theta 2. So vertical component is going to be cancelled, and only cos component is going to be 2b cos theta. B1 is magnetic field at this particular end, magnetic field at this particular end. This is the net magnetic field. You can say B1 sine theta 1 and B1 sine theta. So, or you can say B1, B2. If it is B2 are equal, so they are equal and opposite, so they cancel. This is going to be added down. R is this. Cos theta, automatically you get it. Cos theta is nothing but B by H. This is your B, and that is your H. Okay. So, putting everything, you get this formula. Nothing more than that. Is this clear, everyone? I'm not going to derive the completely, but using this mu naught I L upon 2 pi r, because of this length, you don't even need to put this length maybe. Okay, so there is a this and cos theta. So the cos theta, okay, cos theta is going to be L. Okay, wait. Now it is correct. Put the value of mu naught, which is pi. Mu naught value is not putting here. I r square upon 2 r square 2 pi r or 2 r. Give me a moment, because wait, magnetic field or loop. B sin theta IDL, on the axis. This is the formula for axis. And that's how we can define that. Just give me a second. Wait. Okay, I can wait. Now this. Okay. So after the class, you can see that in this way there is a formula mu naught by 2 I r square z square plus r square, because this is r, this is z. Here they took this as a z, but in our case we took L. Clear? So just revising this, r equals to z square plus r square, or you can say L square plus r square, or for this segment is going to be mu naught I by 4 pi, I mean mu naught by 4 pi I s cross r. This is Biot-Savart law. Simply mu naught I into r del s, or you can say mu naught I L upon 4 pi r square, and then it is cross product is going to be sine theta, and then putting the value of sine theta, which is r upon z square plus r square, and integrating that. So the whole equation, this particular length, when I'm going to integrate, okay, when I'm going to integrate this particular small length to the entire length, so it gives me 2 pi r, because for any particular loop, if I am taking this much of dl, so the total integration gives me L, and L is nothing but 2 pi r. Okay, so in this way you can find this. I already derived this, so you don't need to do this or do this. Just give me a minute. Is this clear, everyone? How we can get this formula? For the formula, you can take the help of this particular derivation, what I already given to you. Because this sine cos thing is going to be taken as a little bit complex process. You can do that simply with the help of Biot-Savart law, with the help of Biot-Savart law and integrating this loop simply. Okay, so this is your formula for this. We can treat this as a formula number 1. Then moving ahead, current loop as a magnetic dipole. For simplification, let us assume that the distance of point P, this is here again point P, is very far away from the current carrying loop. Means if we take this, L is very large than R. So beta take R, take L square common. So that is R upon L square. So this formula is going to be converted into this. Okay. From which formula we arrive this? From this. Similarly, magnetic field B equals to mu naught upon 2 I R square upon R square plus L square to the power 3 by 2. If I take L square common, so I get this 2L to the power 3 R by L square plus 1, and already I write it down this. Wait. Yeah. R. So then this R by L is very less than 1, and we take this whole equation is 1 plus 0.00001 almost 1. Clear? So that is why that is the sign of almost, not equal. Almost equal to mu naught I R square 2L, putting the value of okay, putting here pi and 2 and then 4 pi just to loop group. Okay, is this clear? Why we are doing that? Multiplying, this is your area pi R square, this is your I, so we can convert again into the magnetic moment B. We are going to find the magnetic field into the form of magnetic moment. So R very less to L, A is pi R square. So we know this B equals to mu naught by 2 L to the power 3 I R square, multiplying pi and dividing by pi. So pi R square gives me area mu naught I, or multiplying by 2 pi. Okay, mu naught 2 I pi R square. Sorry. 2 pi divided by 2 pi. So I am just multiplying by 1, nothing more than that. Okay, and then this becomes 4 pi L to the power 3. Wait. 4 pi L to the power 3. So this term becomes A, area, and that is your magnetic moment. Why? So I into mu, I into A. This mu is magnetic moment. I can use this color that much. Mu is I into A. A is A. Okay, mu is IA. So this is your, we do this to find the magnetic field into the form of, in terms of magnetic moment. And there is a same formula for electric field, which is I upon 4 pi epsilon naught 2p by r to the power 3. Same. Clear? We have a formula for electric field whenever a dipole is situated in a magnetic field or putting into the magnetic field. Is this clear, everyone? Okay. Okay. From the previous thing, I repeat everything. See. Okay. This one is your first equation. We have any particular. Oh, wait a minute. we have this particular loop. For this particular loop, we're going to find the magnetic field P, magnetic field at this particular point P, which is L length away. So this is your formula. How we can get this? From this formula, from in this way we get this. Moving ahead, there is a case where L is very, very greater than R, means this particular point is very, very far away as compared to this radius R. So then we're going to find this particular formula. Now on the next page, what I am doing, multiplying and divide with the 2 pi r square, or you can say 2 pi only. So then pi r square becomes my area, and then area into current gives me magnetic moment, which is I into A. So I can find my magnetic field with the help of magnetic moment with the equation 3, mu naught upon 4 pi 2 mu by L to the power 3. And in the same way, I have a electric field formula 1 by 4 pi epsilon naught 2p upon r cube. And this is your magnetic field. Okay, this is your magnetic field at axis or at axial point. We have one more point at equatorial point, but that equatorial point is not going to. At equatorial point, this 2 is going to be removed. I think they don't give you. Wait. No. Okay, but I'll let you know. I give the derivation. I know this thing quite good, memorable one. This is your electric field at an axial point. In the same way, we have magnetic field B. This is B. Is mu naught upon 4 pi L to the power 3 mu only. Okay. This. Okay. Instead of so this mu is nothing but magnetic moment, and this is for equatorial point. This is your at equatorial point. What is the meaning of this equatorial axis? Can anyone please tell me? Tell me, anyone. Instead of this particular perpendicular, if I draw this, suppose this is your loop, okay, and instead of the perpendicular thing, if I draw this, so this is your equatorial point. Clear one? Because whenever a current carrying loop in this way, so your magnetic field is going to be perpendicular. Here is the magnetic field. Don't confuse here. Why should I say equatorial? Equatorial means nothing as such perpendicular. Okay. So if I do this, beta, so this particular point P is equatorial. Equatorial means perpendicular. Perpendicular. And as you can see, this is your magnetic field direction. Okay. So on this particular point, this is your axial point. Axis, on the axis of magnetic field direction. This is. Clear everyone? That is the thing. Is this clear everyone? Good. If it is clear, so solve this one quickly. A circular coil of 100 turns, each turn of radius this centimeter carries a current of this much. What is the magnitude of magnetic field B? Simple. At the center of coil. Now one more thing, at the center of coil, L is going to be 0. Hint. Solution is, as we know, magnetic field B is nothing but mu naught 2I R square upon 2 I R square. Okay, I do R square plus L square to the power 3 by 2. This is your formula, na? So now everything is given. Coil of 100 turns. So you just multiply N also. Now this is your formula. N is given, R is given, I is given, and at the center. What is the meaning of saying at the center? Nothing as such. L is 0. at the center L is 0. Clear beta? So the moment you put this, your magnetic field becomes mu naught I upon 2R. And do that, put the value and get the result. And the result is given this, and this is your magnetic field. Mu naught 2 pi NL upon 4 pi R. 2 pi, 4 pi cancel each other. And as simple as that, the moment I write this particular formula, mu naught, what I write, Ni upon 2 pi or 2R only, not pi. It's your choice what particular values you're going to take. Clear everyone? Is this clear beta everyone? Just turn on your cameras. Clear na? But still, it is quite a doable thing. Nothing I'm doing that much speed so you cannot understand. Okay, so now this question, magnetic dipole moment for rectangular loop is. This is very easy. You tell me this one. Everyone just turn on your cameras, please, everyone. And meanwhile, who did this particular numerical? So they, I already discussed that. Sorry. Okay. Find the correct one and go to that particular test link and attempt the test. There are 6 questions, class assessment, in a class assessment, and you need to do that. Is this clear, beta? Kaila? Sometimes I read your name Koyal instead of Kayal next time. Koyal is a bird name, Hindi name of any particular bird. Look like a crow bird, but sing very well. Maybe you read that particular story or not in Hindi.
Hello, Vishwanath.
Vishwanath.
Yeah, he's not. What is this?
Tell me what is this?
Hello, can you hear me, sir?
Hello. Yeah, hello, Vishwanath. Turn on your camera.
Sir, I don't have camera in that laptop, sir. It is very old laptop, sir.
Oh. So that's why you're not.
Yes, sir.
Yeah, okay.
If I turn on also, it will not be visible, sir.
Oh. Okay. And Sayyid Adil, please turn on your camera.
Everyone, please turn on your camera as it is required, as I already discussed with so many times. Okay. So, magnetic dipole moment of a rectangular loop is. Tell me which one is the correct one. A, B, C, D, and please select the correct option. Inversely proportional to the current. Inversely proportional. What particular options I already give? Kidding. I mean, this question is not going to do. D. I'll tell you. Parallel to the plane of paper. Perpendicular. Okay. As we know, magnetic moment equals to NIA, M directly proportional to A, and magnetic moment is perpendicular to the plane of paper, proportional to the area of loop. As simple as that. Clear, everyone? So we are done with the theory part. So in this, we just recall about the toroid, the ampere, what is current and what is the force between two current carrying wires. Torque on a rectangular current loop in a uniform magnetic field, and circular current loop as a magnetic dipole, and the magnetic field of that particular thing. Again, I am repeating this so many times. Sometimes, where is this? Yeah, not this one. Not this one. At equatorial point, okay, this is your magnetic field. So that is quite observable thing. B equatorial or magnetic field due at equatorial point is half of magnetic field at axial point. And the same thing we know in electric field also, for electric field formulas also. Again, I am repeating, this is here the equatorial point looks like a axial point or axis point, or this particular point Q, this particular point Q is a axial point. Okay, everyone, clear?